Good day, Math 31 students. We have been looking at methods of integration. And in today's lesson, we are going to look at a strategy that's called partial fractions. To set us up for this lesson, I would like you to take a look at question number 1, where you have two rational expressions. I would like you to simplify them by writing them as a single rational expression, and then use the information that you get from question 1 to evaluate the integral in question 2. So you can pause the video at this point, work through questions 1 and 2. When you're done, you can continue the video. Question number 1 should have been pretty straightforward. Get a common denominator and then subtract the numerators. And what we end up with is the integrand. That's what this part is called in question number 2. So question number 2 doesn't look like we can easily find the antiderivative. The numerator doesn't look a ton like the derivative of the denominator, which means that substitution isn't going to work. But if we can take this rational expression here and separate it into two separate rational expressions, then we have a more manageable question. So I can take the integral of these two rational expressions separately, and what we'll find is, since we have linear polynomials in the denominator with a leading coefficient of 1, we can just say these are going to be logarithms. So down here we can see our answer. It is 2 times the natural logarithm of x minus 1. There is our denominator. That 2 is the coefficient. Minus, from here, the natural logarithm of absolute value of x plus 2. This denominator that was part of the second rational expression. Now, if you weren't convinced that we could jump right from this line up here to this final answer down there, we could have done a substitution, where here we'd say u is equal to x minus 1, and so du is equal to dx, and then we just show that we have 2 over u du. And so the antiderivative of 2 over u will be 2 times the natural logarithm of u, but u is just x minus 1. Similarly here for the second rational expression. So this is what we want to learn how to do today. We want to learn how to take a rational expression like this and separate it into 2 or 3 or more rational expressions that are simpler. That is where this lesson will take us. And we begin by looking at a situation where the numerator is of lower degree than the denominator. So a fairly basic question. Our procedure is shown in this box over here. So first step will be to factor the denominator. So this denominator we can see has a common factor of x. So I'm going to factor it to an x times x plus 1. And then I'm going to imagine that I can write this as 2 separate fractions, or 2 separate rational expressions. When we take something big and we break it down into smaller pieces, we call that decomposition or decomposing. So this isn't the same as decomposition that you used for quadratic equations and for factoring them, but it's a similar idea where we're breaking down this big complex rational expression into smaller rational expressions. So what we'll do is we'll multiply both sides by that common denominator of x times x plus 1. I'll just shuffle this over a little bit so it's easier to see. There's my x and x plus 1. Okay. When we do that, the denominators on both sides disappear. So we get an equation that looks like this. Well, here, this is an equation, a single equation, where we have 2 unknowns, the a and the b. The variable x is something that can be a whole variety of things, potentially. but the a and b are what we want to solve. So we need somehow to break this into smaller equations. And we do that using a strategy called equating coefficients. So on the left side of my equation, we would say that this is a linear term here. So this here, linear term because it has an x to the exponent 1. And then on the right-hand side, we also have a linear term here and a linear term there. Should have used green for that, but oh well, we'll figure it out. So we will look at those linear terms and we'll set them equal to each other, because this constant term and this constant term can't affect what the value of those coefficients are for the linear terms. That gives me my first equation and a relationship between a and b. I'll do the same thing with my constant terms. On the left, my constant is a 1, and on the right, my constant is just an a. So from this, I can see that my a value is equal to 1. Woohoo! I've already solved for one of these coefficients in my partial fraction expression up here. So now we can substitute this into this green equation in order to solve for what the b value would be. Notice that once I get to this second line here, I've just ignored the x's. Since I have 3x is equal to 1x plus bx, I can just ignore the x's. I'm not dividing both sides by x because there's a possibility that x could be 0. Well, I guess for this question there isn't, because x is one of the factors in the denominator. But for other questions, there's always that possibility that 0 could be a value for x. So what I'm doing is I'm ignoring the variables and just equating the coefficients on the left to the coefficients on the right, that is, and then solving to get b is equal to 2. So there is an alternate way of doing this. And this is substituting the non-permissible values into the equation. So as you look back at our equation up here, we have x can't be 0, and x cannot equal a negative 1. If I was to take those and plug them into this equation here, what would happen? Well, when x is equal to 0, I'd have 0 plus 1 is equal to 0 plus a plus 0. Oh, so a equals 1. And then if I plug in negative 1 for x, on the left I'll have negative 3x plus 1. And then I'll have a negative a plus an a, and those two a's cancel out, so that I don't have a's on the right side of my equation anymore. The negative a plus a cancel out, and I just have this negative 2 is equal to negative b, so b is equal to positive 2. This is kind of a nice strategy. It doesn't always work this simply, but often it does. So not a bad strategy to learn and to make use of. So that's an option. And we can use that to figure out our values for a and b in this partial fraction expression here. So now I can rewrite my original rational expression, my integrand, as the sum of these two separate fractions. So there's my a value of 1, my b value of 2, and I can take the integral of both sides. And just like in question 2 from the warm-up, I will get some natural logarithms. So antiderivative of 1 over x is the natural logarithm of absolute value of x. And the antiderivative of 2 over x plus 1 is 2 times the natural logarithm of absolute value of x plus 1. If you need to go back and re-examine this question just to make sure you understand the process, you should pause the video here and then work through the question again and take note of the steps that I did. When you're ready, restart and we'll move on to the next question. With this question, we're still looking at a situation where our rational expression has a numerator of lower degree than the denominator. But we have repeated factors. So there's a slightly different strategy that we can use this time. So when I factor my denominator, I can factor out an x squared. Since x is a repeated factor, on the right-hand side, I can say it could be a over x plus b over x squared plus c over x minus 1. You can get away without using this strategy if we were to just take and rewrite our expression as ax plus b over x squared. What I didn't mention in the first question is because our numerator is lower degree than the denominator, we just need to set up our partial fractions so that the numerator is lower degree than the denominator. So here, my numerator is degree 1, my denominator degree 2. I wouldn't make my numerator degree 2 because here my numerator is lower degree than the denominator there. If what I have in red, if we were to expand this out, again into two separate fractions, the ax over x squared would reduce to a over x, and then the b over x squared would give us this b over x squared. So if you don't remember this strategy, that's fine, as long as you remember to make your numerator 1 degree less than the denominator. We have to consider, since our denominator is a quadratic, that our numerator could have a linear term, and it could have a constant term. The math can tell us if one of these two is 0, but we assume that the terms are there until the math tells us otherwise. I'm going to continue with the method that we have in blue. So when we multiply both sides by this common denominator of x squared times x minus 1, here's what we get. And then we will expand to get rid of those brackets, and this is what we have. Now notice on the left side, I put in some placeholder terms. On the right side, I have some x squared terms. On the left, I didn't. So I'm going to assume that I have a 0 x squared on the left. And similarly with the linear term, on the left, there wasn't anything. On the right, I had a minus ax plus a bx. Now we will again equate coefficients. So I look at my quadratic terms, and on the left, my coefficient is 0. On the right, I have an a plus c. So those are the coefficients of the quadratic terms on the right. Similarly, on the left, I have 0 x's. On the right, I have negative ax plus a bx. So again, I ignore the x's and just equate the coefficients on the left and the right. And similarly, the constant term on the left is a 1, on the right a negative b. And so that's where I will start for solving to figure out the values of a, b, and c. So my b value will be a negative 1. Once I figure that out, I plug in a negative 1 here, solve for a, and I get a is also negative 1. Once I know a, I can solve for c and discover that my c value will be a positive 1. So I didn't show the details there, but you can figure it out. If you need to pause and work through those details, feel free to do that. Otherwise, let's continue. Here is my decomposed integral. So from up here, my a value is a negative 1, b was negative 1, c positive 1, and here I have those coefficients in these integrands for the question. The first one will be a natural logarithm. The second one, watch out, because once we do a number of these, we get assuming that we have natural logarithms. But for this one, the antiderivative is not a natural logarithm. So again, we can think of this as having been a negative x to the negative 2. And so we'll add 1 to the exponent, which makes it a negative 1. Divide by the new exponent, the negative over negative, makes it a positive. But there we have the integral of the question that we started with in number 4. If you need, pause, look back over the question, make sure you understand the details of every step, this strategy, or you could do it from this strategy as well, what we have in red. When you're ready, continue the video. All right, getting a little more complex here. Again, I've factored my denominator, but I have this factor in the denominator that's a quadratic, degree 2, so I need a degree 1 or a linear factor in the numerator. Again, my initial question, the numerator was lower degree than the denominator, so I just need to make sure these two partial fractions have a numerator which is lower degree than the denominator. When I multiply both sides of the equation by the common denominator, here's what we get. And again, I've color-coded just to help us recognize the like terms. So the blue terms are quadratics on the left and the right. The red terms are linear on the left and the right. Notice the left didn't have a term, so I put in that placeholder of a 0x. And then my constant terms are green. So I look at those three, and that gives me three equations. I can see right away that my C value is 0. So again, I didn't assume that any of these terms didn't exist, but the math tells me that the C value is going to be 0 for this question. And then as we solve, here we can solve to get an A value of -1 from this constant equation. Plug that into the quadratic equation, and we'll get that our B value has to be a 2. So here is what our decomposed fraction looks like as we're going to do the antiderivative. For this first one, that'll be straightforward. It'll be a natural logarithm again, but the second one, because it's quadratic in the denominator, is not a natural logarithm. So what I'll want to do is a substitution, because I see my denominator has an x squared. Its derivative is a 2x. There's the 2x in the numerator, so I can see the derivative of the denominator in the numerator. So I'll substitute, letting u equal x squared plus 2, and then find my differential du to be 2x dx. Since I have my 2x dx here, I'll just circle it. There's my 2x dx. That part will be replaced with a du. And then this whole denominator will become just a u. So I'll have 1 over u times du. There we go. When I find the antiderivative, that'll be natural logarithm of absolute value of u. I stuck in the plus c already, although if you leave it to the very last line, that's okay, because we do need to back substitute, replacing this u with x's, since our original question only had x's. Our u is equal to x squared plus 2, so there we have our final antiderivative. When you're good to go, flip the page and we'll continue on with the next question. We have one final example before a couple check your understanding questions. So here we have case 2, where the numerator is not of lower degree than the denominator. Same degree means we need to take an additional step. Or higher degree, we would do exactly the same thing. What we'll do is we'll actually do some long division in order to simplify this expression a little bit. So we will divide the denominator into the numerator. And you'll recall that what we do is we look at this first term only and we say, what do I multiply 2x squared by to get 4x squared? Well, the answer is 2. Typically, we'll align the like terms one above the other, so the constant is above the constant. Then I'll do 2 times this blue divisor. 2 times 2x squared is 4x squared. 2 times 3x is 6x. 2 times 1 is 2, and then we will subtract. So we have a quotient on top here is 2, And we have a remainder on the bottom, which is negative 5x minus 4. So that means that we can rewrite our original rational expression in this way, where I have the 2, which is my quotient, and then I'll add the remainder over the divisor. So it's kind of like when you do mixed numbers. So if we had 2.5, we'd have the 2 and then plus the half. Here, now we have a situation where the numerator is lower degree than the denominator. And so the strategy is just like we were doing for the previous question after this initial step of doing long division. So why don't you pause the video at this point, work through this question, and then once you're done, restart the video to see my solution. So pause now. Here we go. I'm going to focus just on this rational part here, and then I'll deal with this integral of 2 a little bit later. So I can decompose this into partial fractions. I have 2 linear factors in the denominator. So my numerators can be constant terms. And then when I multiply both sides by the common denominator, here's what I get. I have linear terms and constant terms on each side of the equation. So with my linear terms, I'll have the negative 5 on the left, and on the right, a plus 2b. So again, I'm ignoring the x's, just equating the coefficients. And then similarly, the constant on the left is a negative 4. On the right, I have an a plus b. So we have a little bit more complex linear system for us to solve here, but it's really not bad. Here, these two a's have matching coefficients of 1, so I can just subtract the two equations. And when I subtract, 2b minus b is b, and negative 5 minus a negative 4 will give me negative 1, so my b value is a negative 1. If I know b is negative 1, I can back substitute to get a is a negative 3. So I have my values for a and b. So here's my integral. Now I'm including that integral of 2. So don't forget this part. Easy to forget it because at this point we focused only on this rational expression, but don't lose track of that integral of 2 dx. We need to find that as well. And so then we can do the antiderivative here. You may have used substitution for this middle term here because we don't have a coefficient of 1 with the x, or you might just recognize that when we take the derivative of this, where I have the 2x plus 1, the derivative will have a 2 in it. To undo that, I need to divide by 2 here. But again, you could do substitution to do this antiderivative. And there's your final answer. Now, sometimes there are some other shortcut strategies that we could take. So in this case, we could have actually broken this down slightly differently in order to solve for our a and b values. So here's what I could have done instead for this question. And again, this isn't a strategy that always works, but sometimes there are some shortcuts. What I'm going to do to begin with is I'm going to take these negatives in the numerator here, and I'm just going to factor them out to make this a subtraction sign out in front. So then I'll have a positive 5x and a plus 4. So these will both be positive here. Why? Well, I wouldn't have had to do it at that step, but it's going to make what I'm going to do next a little bit simpler. 5x is the same as 2x plus 3x. And 4 is the same as 1 plus 3. Well, why did I want to do that? Because my denominator has a 2x plus 1 in it, and it has an x plus 1 in it. So what I could do is I could separate this into this fraction, or rational expression, and, well, it looks like this. They will have the common denominator, but I'm going to separate the numerator part. So maybe I shouldn't have shown it like that. Instead, I'll show it. I'm going to group this part together and that part together, and then put them over the denominator. So I'll have 2x plus 1 over top of 2x plus 1 times x plus 1. And we can see from here that the 2x plus 1's cancel out, and I just have a 1 in the numerator. So looking down to the bottom here, that's this term, the 1 over x plus 1. This has the negative, but remember, I put the negative out in front of the integral here. So it would come back into play once I rewrote this here. Similarly, as we look at the second rational expression, we can factor the 3 out in the numerator and have an x plus 1 all over 2x plus 1 over x plus 1. And I see now that these x plus 1's cancel out. And so I have 3 over top of 2x plus 1. Well, notice down here in blue, I have a negative 3 over 2x plus 1. Again, the negative sign I had initially factored out over there, so it would show up again in front of my integral sign. So sometimes you can do a strategy like this, which saves you from doing this work of equating coefficients and solving linear systems. So that's something you might want to watch for to see if there are times that you can make use of that. All right, the next page has a couple of check your understanding questions. So why don't you pause the video at this point, review these questions, make sure you understand them, and then work through the check your understanding questions. Once you're done, you can restart or continue the video. Here we go with question number 7. Our numerator is higher degree than the denominator, so we need to begin by doing some long division. Here's what I get: a quotient of x minus 1 and a remainder of 2. So that lets me rewrite my original integral as the integral of the quotient plus the integral of the remainder over the divisor. And when we do those antiderivatives, here's what we come up with in our last line. Looking at question number 8, we have an interesting thing that happens here, where once we factor the denominator, we see that there's a common factor in the numerator. So there's a non-permissible value here that we need to keep in mind when we write our final answer. So here I'm going to say x can't equal a negative 1 because that's the point of discontinuity for this function. But then I go through the typical steps. I only have the 2 factors that I have to deal with since we had that common factor canceling out. I solve to get values for a and for b, and then I can write my decomposed integral. And there's our final answer. But then again, we do want to state that x can't equal negative 1 because it would be a permissible value as given the equation or expression that we have here. So absolute value of negative 1 would be positive 1. We can take the natural logarithm of positive 1. Negative 1 minus 1 would give us a negative 2, but the absolute value is positive. We can take the logarithm of a positive 2. But this will be undefined where our original rational expression was undefined. There we go. That is partial fractions and integrating using partial fractions. Take care.